Okay, so in this problem, we're given some molecules, and our task is to find whether they're polar or nonpolar. So to start off, you always want to draw the Lewis structure, and I'm going to start off with OF2 because I like that one. We have 20 valence electrons. So we start out by putting those on the outside atoms. After those are filled, we fill up inside atom. So, also, you want to put the least electronegative atom in the center usually. That's why I drew it this way. So now that we have the Lewis structure drawn out, we can assess the electronegativities. So F has greater electronegativity than O, so we have a dipole going this way and a dipole going this way. At this point, you would think it would be nonpolar. However, you have to account for the domain geometry. We have two non-bonding pairs, so this will actually be a tetrahedral, and that would look something like this. Oops. Something like this. So our molecular geometry is actually bent, and obviously the dipoles will not cancel out at this point, and we'll have a net dipole going down. This leads us to believe that this molecule is polar. Okay. Let me erase all this. Sorry, I don't have a large eraser. Our next molecule is SO3. And I already have the Lewis structure drawn out, so I'm just going to go through it real quick. Now we can look at the bond dipoles and assess that O has greater electronegativity than S. So in fact, the O's will have a partial negative charge. I believe I forgot to include that in my last Lewis structure, but so they have partial negatives, and this has partial positive. And since we only have 3 domains, this is actually trigonal planar, and the dipoles cancel out for a net molecular dipole of 0. So this molecule is in fact nonpolar. Okay. Now let's give it a go with our tiny eraser again. We have BeCl2. So in this structure, Be does not actually need an octet because it's a special case. And the molecule is perfectly happy this way. Electronegativities of the Cl are greater, so this is partial negative charges with a partial positive in the center. And since this is linear, we don't have to draw the since this is linear, this is actually also the molecular geometry. So the dipoles cancel for a nonpolar molecule. Now we have CCl4. I've already drawn the Lewis structure as well. And since Cl is more electronegative, all of these will have partial negative charges, while the carbon has a partial positive charge. Now, all these bond dipoles are going towards Cl's, and since this is tetrahedral, it will look something, hold on. It'll look something like this. And since all of these domains are the same, the dipoles will cancel for a net molecular dipole of 0. And that will, in fact, be nonpolar. Okay, so our next molecule is O3. And I already have the Lewis structure drawn. So, let me get that down real quick. And looking at this, we have a bent geometry because we have this lone pair. So the molecule actually looks something like this. And from this, we can gain that this has a dipole, net molecular dipole going down. So this molecule is actually polar. So some common problems I run into are not counting the actually, like, so I'll get like, so this one has 18 valence electrons, and I'll establish that, but when I actually start drawing the structure, I'll maybe not include a bonding, not include a pair of electrons, or not include something, but I'll think it, I don't know, I just get confused that way sometimes. I like to use J-Hop's method of counting, which is counting each pair and bond and then doubling the number. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 2 gets us to 18. I find that's the simplest method to avoid that error. And another error would be not realizing that you have, not really realizing that this structure is actually bent, thinking it's linear and believing it's nonpolar when actually the structure is polar. So just watch out for non-bonding electrons, and make sure you're counting and drawing the correct amount of valence electrons. And that should be it. Thank you.